Hi, I've had a bit of a shout out for a topic, calorimetry, that comes from paper 1. So what's calorimetry? Well, first of all, it's a piece of apparatus called a calorimeter. And a calorimeter couldn't be any easier. It's a beaker with water in it and a thermometer. That's all it is. And the beaker of water with the thermometer in it is measuring a temperature change. So underneath the beaker, you've got something that's making heat. It's a fuel. It could be ethanol. In this case, there's a spirit burner with ethanol in it. But it could be anything that's burning. It could be, I don't know, a peanut that's on fire, or a chip that's on fire, or a candle. It could be anything that's on fire underneath making heat. And the heat heats up the water. The water is registered, the temperature change is registered with the thermometer, and that's it. So the fuel, whatever it is, heats up the beaker of water, and the thermometer tells you how much the temperature has risen by in the beaker. We want to measure the temperature of the water as it's being heated up. So we don't really want any of the heat to escape. We want all of the heat to go into the water because we're measuring the heat change in the water, the temperature change in the water. So we could do with minimizing the heat loss from the beaker. So quite often what we do is we put a lid on it to stop any heat escaping out the top, and we might put some cotton wool or something around the outside, or some polystyrene, try and insulate the beaker as well to stop any heat loss coming sideways through the glass beaker. Okay, so we have an equation, and it looks complicated, but it's really not complicated at all. Delta H. Delta is the Greek letter D, and it looks like a triangle. It means change. Change in heat. H for heat, triangle change. Heat change. Okay. Sometimes it's called enthalpy change. Another word for heat is enthalpy. Enthalpy change or heat change. We're going to measure how much heat is given out by this fuel. That happens to be ethanol, but as I say, it could be anything. We're going to measure the heat change that's produced by this fuel. In other words, we're going to measure how good a fuel is it. So we're heating it up, and I know that ethanol is a really good fuel, whereas something maybe like burning a peanut is not that good a fuel. A candle is okay, but ethanol is a really good fuel. So we'd expect that the heat change produced by a really good fuel like ethanol to be quite high compared to a candle or compared to something like a burning peanut. Okay, so we're measuring how good a fuel it is, what the heat change is coming from this fuel. Okay, how do we do that? It equals minus mc triangle T. Why a minus, first of all? Well, a minus means that this is exothermic, giving out heat. So we need a minus in there because the minus tells you that there's an exothermic reaction going on. Something is giving out heat. M. What's M? M stands for mass. Now, lots of people get this wrong. The mass is nothing to do with the mass of the burner. Never, never, ever. It's to do with the mass of the water that's in the beaker. So M is the mass of water that's in your beaker. Nothing to do with the mass of the fuel that's being burnt. We'll get to that in a bit. C. C is just a number. It's a number 4.18. It's a measure of how easy or difficult something is to heat up. So water has got a number 4.18. It tells us how easy water is to heat up. We need that number in there. It's actually called the specific heat capacity. It's a measure of how easy or difficult the water in the beaker is to heat up. And it's always given to you. You never have to remember 4.18. It will just say the specific heat capacity is 4.18 or C is 4.18. So it's just a number. Don't worry about it. Triangle T. Remember, just as before, triangle delta, the Greek letter D, stands for change. Change in T is temperature. So let's say the thermometer started at 10 degrees C and went up to 30 degrees C. So it's gone from 10 to 30. 30 take away 10 is 20. It's gone up by 20 degrees Celsius. Okay. The temperature change is in degrees C. It can also be in Kelvin if you want. It doesn't matter. I'll try and explain that because sometimes people ask me that. The temperature change is the same in degrees C and Kelvin. Let me prove that to you. 0 degrees C is 273 Kelvin. 0 degrees C, if it goes up by 25 to 25 degrees C, the Kelvin goes up by 25 as well, from 273 to 298. So the temperature change is the same in degrees C or Kelvin. It's just that the two scales of temperature are offset. They're both offset by 273. If you don't understand that, it's fine. The temperature change is in degrees C or Kelvin, the same thing. Okay? And we need to measure the temperature change. Sometimes you see this equation. It's almost the same. Instead of delta H, you've got Q, and you've got no minus sign. Sometimes in a textbook, you'll see that. It frustrates me as to why it even exists. If I ruled the world, I'd get rid of that equation because it's a poor person's version of this equation. Q is delta H, but it doesn't tell you whether it's exothermic or endothermic. So Q is another way of saying heat change, but it's not positive or negative. The negative isn't in there, and you never really know with Q whether it's giving out heat or not giving out heat. So if you see this equation, I would tend to ignore it and use this one instead. Delta H is minus MC delta T. So Q is just something you'll see in a textbook, and it annoys me, it frustrates me, because Q is delta H without the minus. Okay, it's a measure of heat change, not knowing whether something is giving out heat or taking in heat, exothermic or endothermic. So if you see that, I'd ignore it. Let's stick to the top one, a much more useful equation. Delta H equals minus MC delta T. Okay, let's imagine that the mass of the water in there was 50 degrees C. Sorry, 50 grams. The mass of the water was 50 grams. Okay, let's do a minus MC delta T minus 50 minus multiplied by C, which is 4.18. It always is 4.18 multiplied by the temperature change. Well, let's say the temperature, the thermometer measures 10 degrees C and ends up at 30 degrees C. Temperature change is 30. Take away 10. 20 degrees C is how much the temperature has gone up by. So let's multiply it by 20. Minus 4180. Okay. So the ethanol has given out, because it's minus, 4,180, and it's measured in joules. 4,180 joules. Let's write that down. So my ethanol gave out minus 4,180 joules. Okay. It's not quite that simple. I need to do something else. I need to measure the mass of ethanol that I've used. Because let's imagine it was a match that was burning and a bonfire. A match and a bonfire are both wood. But clearly the bonfire is going to give out more heat than a match, just because there's more wood. So we need to know how much ethanol has burnt so that we can give it a fair test. And when I measure the mass of the ethanol that's been burnt, the mass of the burner has gone down by 4.6 grams. So 4.6 grams of ethanol was burnt. I measured the mass at the beginning and the mass at the end, subtracted it, and I worked out that 4.6 grams of ethanol was burnt. So that it's a fair test, I need to know the number of joules per 1 mole of ethanol burned. So I've got to have it as a mole, because otherwise it's not fair. If it were a match burning compared to a bonfire burning, I need to compare the amount so I can work out how good wood is as a fuel. Yeah? So I need to work out how much ethanol I've burnt, because if I use a little bit, it's going to go up, the temperature's going to go up a little bit. If I use a lot, it's going to go up a lot. So I need to make a fair test and work out how much heat is given out when 1 mole is burnt. I've got 4.6 grams of ethanol. I need to work out if I've got a mole or less than a mole or half a mole, quarter of a mole. Well, I know that moles equals mass divided by MR. The mass of ethanol that's burnt is 4.6. If I work out the MR of ethanol, CH3CH2OH, that's 2 carbons, 12 each is 24, 6 H's, 1 each is 6, 30, add an oxygen, which is a 16, 46. Well, that's convenient, 0.1. So I have got 4,180 joules burnt when 0.1 mole of ethanol is burnt. I want to know how many joules would that be if 1 mole was burnt. Well, 0.1 mole of ethanol is 1/10 of a mole. So if I use 1 mole, that would be 10 times more. So if I used a whole mole, and that's what I need to measure or work out so that I've got a fair test, I'm going to times by 10 for when 1 mole is burnt. So I work out this, delta H equals minus MC delta T, where M is the mass of the water. I then calculate, once I've got my number of joules, how many moles of fuel I've burnt. In this case, it's 0.1 of a mole. Scale it up to how many it would be if I had a whole mole, which is 10 times more. So that'd be 41,800 when 1 mole was burnt. And sometimes it asks for it in kilojoules. Joules, kilojoules. Joules is smaller than kilojoules. If I go from small to large, I divide by 1,000. So small to large, divide by 1,000. If I divide by 1,000, 41.8 kilojoules of energy is given out when 1 mole of ethanol is burnt. Sorry, fat fingers there on my keyboard. 41.8 kilojoules when 1 mole of ethanol is burned.